Hey, how's it going? What I'd like to do tonight is I'd like to go over a quiz, an old quiz from a previous semester, so that you can get an idea of the kinds of questions that I ask on a quiz, the sort of things that I'm looking for when I'm grading, and maybe so it can alleviate a little bit of the anxiety of the first quiz, all right? So I'm going to go through this just the way I'd go over a quiz after I give the quiz in class. And, just pay attention to the sort of things I'm looking for and the sort of things I'm saying, because it'll give you a hint on the sort of things that you might see on the quiz that you take. Now, this particular quiz was given in a small class, which means it has a wider variety of questions than those that might be in your particular class. If you have a lot of students, I might get rid of the short answer questions, for example, and just make them into more multiple choice questions. But still, they should give you a general idea about what's going on, all right? Here's the first question on the quiz. A pipe carries water through a junction. Which of the following could be units of the mass flow rate? The quantity of water that moves through the pipe at any given instant. See in the upper right-hand corner, I also give you a formula for the mass flow rate. In this case, the mass flow rate is equal to the density of a fluid times the cross-sectional area of the pipe and the speed of the fluid through the pipe. So you don't know the units of the mass flow rate. You probably should know the units of density, the units of area, and the units of speed. So that means that you should be able to find, through dimensional homogeneity, the mass flow rate. This is the kind of question that you might see starred in the conceptual questions on your homework, remembering that the quizzes are just a test of whether or not you're doing the homework. That means that instead of having the actual formula in the homework, it's a slightly different formula, and I'm looking at the skill instead of just whether or not you answered the question. I think in the homework this is probably F equals ma, so this is a slightly different problem, but you still should be able to answer it. Now, how would I systematically go through this using dimensional homogeneity to figure out what the units of the mass flow rate are? Well, the first thing I do is I'll just rewrite the definition of the mass flow rate. Then I'll equate dimensions using dimensional homogeneity. I'll split up the dimensions on the right-hand side, substitute the dimensions for each of the quantities. I'll recombine the dimensions by multiplication, and then I'll substitute in the SI units. A lot of this you can probably do in your head. If not, you can do it in a lot simpler way if you've been doing this a few times, but this is how you do it systematically so that you're sure that you get the right answer. All right? So here we go. We just rewrite the same thing. Then I equate the dimensions using dimensional homogeneity. You see that all I have to do is put the little brackets there. Then with the brackets, I can separate each of the terms out, so that I'm looking at the units of density times the units of area times the units of velocity. Then I substitute in the dimensions, which are those MLT, mass, length, and time. So the density is mass per unit volume. Mass, you can just use mass. Volume is, length times width times height. So that has dimensions of length cubed. Per, obviously, is 1 over, so you have ml to the minus 3. The area is just the length times the width, so that's your L squared. Your velocity is meters per second, or length per unit time, right? So distance per unit time, length per unit time. So you can just multiply all those out now. And if you multiply all those out, you see all of those lengths cancel, so you just have m t to the minus 1, m over t, mass per unit time. The units of mass in SI units are kilograms. The units of time in SI units are the second. And therefore, you have the units of the mass flow rate being kilograms per second. So that would be C. All right. So I think that's probably sufficient to give you an idea about how to do this particular problem. Okay, let's see what happens when we go to the second problem. Okay, the second problem has these white dots, and the white dots below immediately the white dots immediately below represent the location of an insect. So that's an insect flying from left to right across your screen. There's a strobe. That strobe is going off at a regular interval. So the time between each one of these dots is the same amount of time. And the question is how do you relate these dots to these graphs, right? So you've got these graphs here, they're right there. And each one of them is a proposed graph for the velocity. So now you look at those and you say, okay, well, which one is it? How would you do that systematically? Well, first you think about what concept it is. It's kinematics. You know that the change in x is equal to the velocity times the change in time. Change in time is constant because of the strobe going off at a uniform rate, right? So it's a constant frequency. Delta t is constant. So that means that the velocity is proportional to the difference between subsequent points in here. So the difference between the point that's farthest left and the next one, distance between that next one and the one just a little bit further off to the right, and so forth and so on and so on. So that gives you an idea about how you can analyze this, right, just graphically. Say the first one is this tiny little arrow. Notice I'm drawing that not just next to the points, but I'm redrawing it below. And I'll redraw the next one below as well. You'll notice that these two lengths are different. That means that A is wrong because A is just a flat line. So A could only be true if both of these arrows were the same length. Also, since the second arrow is longer than the first arrow, that means either of these two bits here, B or C, where the velocity is reducing, can't be true either. So we've eliminated 3 of the possibilities already. We keep on going a little bit longer, a little bit longer, a little bit longer, a little bit longer, a little bit longer. And now you've got something that's a straight line. And since it's a straight line, so is the Vx versus t graph, because delta x is proportional to the velocity. So we have this straight line answer here, which is D. Got that? That's simple enough? I think you probably understand that. So that's basically how I am going through these multiple choice questions. I'm doing them systematically here. You should be able to do them conceptually as well. All right, well, for this third one, I asked a question that said something about figuring out what a physical phenomenon that's not a pendulum or a clock was that you could use a time standard for, and so here I'm just asking you to repeat that. Again, if it's a large class, then I'll just have a bunch of different options for you to choose from. In this case, it was an open-ended question. It was a short answer question, so you got to write down whatever you wanted. Rotation of the Earth around its axis probably would have worked. That's been used as a standard. Oscillations of radiation from an atom, that's actually the frequency standard that we're using right now, and that defines a second. And the orbital rotation of the Earth around the Sun, that's another possibility that's been used. So there are a bunch of options like that. The circumference of the Earth around the equator, things that you could use as a time or a physical standard that you could use. So one rotation of the Earth, anything, 1 day, one month, 1 year, all of these things are possible. Next, we have a more conceptual question. So if there's an object that's thrown straight up into the air, and then it comes back down and feels no air resistance, how can it have an acceleration right up at the top there? So right up at the top of the path, it goes up, it stops, it comes back down. So how, when it goes up, it stops and comes back down, right there where it stops, can it have an acceleration? Well, the way to think about this is to sort of think about the graphs. So we've got the height versus time and the speed versus time here. So you can see, again, that the height is going to go up and then back down. That's what the top graph shows. And the velocity keeps decreasing, and it goes through 0 right there at the apex of the z versus t curve. So these are the things that we have to consider. Now, first of all, we know that the object stops moving only for a moment. Second of all, the acceleration is how much the velocity is changing at that moment. And you can see here that that velocity is changing no matter how small this box gets. And that velocity is actually going to change at the same rate no matter how small this box gets that I just drew. So that the velocity, even at that point, is changing. If it's 0, it's going to slightly change so that it will start moving, right? It's just like anything. In order to start moving, again, something has to have an acceleration because the acceleration is describing the change in the velocity, right? The acceleration is describing the change in the velocity. So if something's going to start moving, then it has to have an acceleration. If it's not going to start moving, it's not going to have an acceleration. So the velocity is constantly changing as the object moves up and down through the air. That's the sort of thing I'm looking for in that sort of question. All right. All right, next I have a check your answer problem. This is a fairly common one I like to ask. In this case, what I do is I give a question and then an answer, and then I ask you to analyze it and tell me why that answer is reasonable or not. So in this case, I've got a car that's sitting at the entrance ramp of a freeway just waiting for a break in traffic because it's, you know, a really busy day. And then as soon as he sees that break in traffic, the driver is going to accelerate with a constant acceleration along the ramp and onto the freeway, get in there, have a great time, get to work, and enjoy his time with you, right? So if that car has a 20 meter per second speed when it reaches the end of the 120 meter long ramp, what is the acceleration of the car? Now, this is something you can work easily. I'm sure this is well within your powers of working. But the question here isn't to ask whether or not this is the correct answer. It's to ask whether or not it's a reasonable answer, which is a completely different question. No, it's not a completely different question. All correct answers are reasonable. Not all reasonable questions are correct. In fact, most reasonable questions should not be correct. The reason why I ask this, of course, is that it's a big part of expert practice to reflect on what you've got as an answer. In fact, you should be reflecting on what you're doing as you're doing it. You should say, does this number make sense? Does this expression make sense? And that sort of thing as you go along. It really helps you a lot if you can find an error when you make it, instead of, you know, if you're in the real world and you're making a real thing a month and a half after you made the error, right? So you should always be looking for these problems. So for the first part, I'm asking about dimensionality. I'm asking if this acceleration has the right units, and the acceleration should have the units of meters per second squared. That's the right units in the SI system to have if you're the acceleration. It turns out that 2.3 meters per second squared has those units exactly, so the answer is correctly stated. All right, and yes, that is good. We're happy with that. Okay, so that's all it is. So this is not some sort of metaphysical question. This isn't something that should make you very freaked out. This is just something that you should be able to think about and reflect on for anything that happens, anything that you're doing while you work. All right. For the next one, you want to figure out if the magnitude of 2.33 meters per second squared is reasonable. We know one acceleration, which is 9.8 meters per second squared, and the acceleration of the car is about a fifth of this, which means that this is probably a human-sized acceleration is probably okay. You know, it's good that you're not going as fast or accelerating as fast as gravity. I don't really know, but I don't think you're usually hitting 1G when you're trying to get on the highway, right? But, you know, you wouldn't want to go too slow either. So we've got here a fairly reasonable idea about why this should be, yes, be a reasonable thing. And just to let you know that this is true, the thing I said at the very beginning is true, I'm going to go through and I'm actually going to solve the problem. So I'm going to go through, solve the problem, just to show you that this is the wrong answer, even though it's a reasonable one. And you'll see that it's reasonable as well. So these are the equations that I pull out of kinematics to solve this problem. V equals AT, x is equal to AT squared. V equals AT is equal to 20 meters per second. So if I have an AT, I can always put in an AT. I think probably the easiest way to do this is to multiply by 1, a over a. And that way I get AT squared over 2a instead of 1/2 AT squared. And that way I can substitute the 20 into the AT squared bit, and I get 400 meters squared per second squared over 2a is equal to the length of the ramp, 120 meters. And this is something I can just solve for. I can plug this into a calculator or something like that, and I get an answer of about 1.67 meters per second squared. So that was a big problem. That is a big problem when I ask these questions, is that a lot of people will actually solve the question, solve the problem, right? Resolve the problem, know that it's wrong, and then say, no, it's wrong, because it's not the right answer. Well, that just because it's not the right answer doesn't mean it wasn't reasonable. So you're trying to build up an intuition about whether or not things are reasonable without having to go through and rework the question. Right, there's an old engineering rule of thumb, 2 out of 3 times is good. So you work the question, you rework it. If you get a different answer, you rework it again, and hopefully that matches one of the other 2 answers, and that's the one you go with, right? That's not really a great way to do things. For one thing, you have to work the question twice. You have to work the problem twice every time you do a problem, which is probably not the best use of your time. So you just want to see if you have a reasonably sized answer, and you want to see if the dimensions are correct or the units are correct on your answer. All right? So I think that'll be a pretty good lesson, right? That's something you should be able to handle right there. Finally, this is always going to happen in physics. You're always going to have something to work, right? You have to work a real problem, because I can't really tell if you're learning about the problem-solving stuff unless you solve a problem. So on a quiz, this is how I'd have this thing look. It's going to be 6 points. The points are 2 points for that first half of the problem, 2 points for the second half of the problem, 1 point for using something in that first half of the problem in the second half of the problem, right? And finally, 1 point for getting the right answer. On top of that, in a test situation, the describe the step thing is going to be blank. So you're going to have to put things in there. That's going to be worth a point to put some text in there on a test telling me exactly what it is you're doing, right? I'd very much like to know what you're doing before I figure out if you did the right thing or the wrong thing, right? So on the test, you'll have perfect freedom to solve the problem any way you want. You just have to tell me what you're doing while you're doing it so I can figure out whether or not you did the right thing, okay? In this particular case, what am I looking for? This is an estimation problem, right? So it's estimate the total number of blinks that somebody's going to perform in their lifetime. How many times are you going to blink? And I want it in scientific notation and all that stuff like that, just to see if you can put things into scientific notation and those sorts of things. So the first thing I ask for is just an estimate, a guess on the quantities that you need. You want the number of blinks in a lifetime. Probably you can't just figure that out by thinking about it. Probably what you have to do is you have to think about how many times you blink per minute. And you probably have 10 blinks per minute. And I screwed up there, okay. And then you want to figure out your lifetime in years. We're going to go with 80 years because we're optimists here. Okay, and that'll give us the number of blinks per minute at 10 blinks. That's what we're going to carry over. Then after that, we can use that to go to the next bit, which is converting the units. We've got 10 blinks per minute, right? And when we take those 10 blinks per minute, we can add a new thing. So we want to go from minutes to hours, then hours to days, then days per year, and then finally years per lifetime. Put that all together and we get some really large number of blinks per lifetime, 420 million blinks in your lifetime. You're going to spend a lot of time blinking in your life. And finally, you want to convert that into scientific notation. It should be 10 to the 8 blinks per lifetime. So that's how you go through and report all this when you're solving one of these problems, all right? Thank you very much.